This is a short video about functional groups. Now, a functional group is a specific arrangement of bonds and atoms. We are going to see that certain types of functional groups appear frequently in organic chemistry. Now, a functional group demonstrates similar chemical reactivity. Some organic chemistry textbooks consider alkanes as the first functional group. Your textbook discusses them but does not list them in the functional groups table. Alkanes are hydrocarbons. They are composed only of carbon and hydrogen. They are considered to be saturated, where you only have single bonds. Alkanes are fairly unreactive. They are unreactive because they have strong carbon-carbon and carbon-hydrogen bonds, and they are nonpolar. There is not a large difference in electronegativity between carbon and hydrogen. When I say they are unreactive, they do react in certain reactions, such as combustion, where you burn them in the presence of oxygen, or radical reactions. And we will deal with these types of reactions later on in the semester, but for our purposes, they are fairly unreactive. Here is table 1.6 or 1-6 from your textbook. You need to memorize this table. You need to memorize these functional groups that are listed here. Now, what we are going to see, just a couple of things to note. Right? Where you see an R designation, what this means is you either have an alkyl group or a hydrogen. So for example, here where you have this acetal, OR could be a CH3 group or a CH2CH3 group. That's what I mean by alkyl. Right? In addition, R could be a hydrogen. Now, you need to know alkenes, where you have one double bond, alkynes, where you have a triple bond, arene or aromatic, where you have a ring with 3 alternating double bonds, an alkyl halide, where X is a halogen, and alcohol, that is an OH group. Now let's look at a phenol. It has an OH group and that arene or aromatic ring. This whole group is the phenol. A thiol, you have an SH, and ether, you have an oxygen between 2 carbons. An acetal, we have 2 ether groups attached. A hemiacetal, one is an OH and one is an OR group. You have to be able to recognize this whole structure as a hemiacetal. It's not a hydroxyl group or an alcohol and an ether. It's a hemiacetal. An epoxide is where we have a 3-membered ring with oxygen. An amine, you have a nitrogen attached to a carbon. Now, you can see there is nothing but bonds on that nitrogen. Okay, you could have alkyl groups to the nitrogens, or you could also have hydrogens, or just simply one hydrogen and one alkyl group. A nitrile is a carbon-nitrogen triple bond. A ketone is a carbon doubly bonded to an oxygen with 2 carbons attached. Now let's make a note. Look at the aldehyde. Again, you have a carbonyl, but here you have a hydrogen. This often defines the end of a molecule. The same can be said for a carboxylic acid as well. So this whole group is a carboxylic acid. It's not a ketone and an alcohol, right? You have an OH group bonded to this carbonyl carbon. So again, let me just say this is a carbonyl. Okay. In an ester, we also see that carbonyl with C doubly bonded to the oxygen, but now we have an ether attached. So this whole thing is an ester. And finally, we have an amide, where you have a carbonyl bonded to a nitrogen. So the whole group is an amide. You're going to practice these in recitation, and I'm going to do a practice problem on the next slide. Here's the structure for strychnine. It is a pesticide. This is problem 1.69 in your textbook. The problem asks you to identify the functional groups that are present in this molecule. So you will be faced with problems of this nature on your exam. So let's go through this step by step. Here, I have an arene. You could also write aromatic, or you could write benzene. So the structure of benzene, I didn't say this in the previous slide where we had our table of functional groups, but this is benzene. It's a 6-membered ring with these 3 alternating double bonds. Again, it depends upon the textbook that you're using. We will encounter this molecule in organic too. All right. So an arene aromatic benzene will be acceptable for that functional group. All right. Now let's look over here. We have this nitrogen bonded to a carbonyl. This functional group will be your amide. Right. Then let's come over here to this oxygen. It is an oxygen bonded to 2 carbons, so that will be an ether. Then here, I have a double bond. That is going to be considered an alkene. And finally, if we come up top, I have a nitrogen that's bonded to 3 carbons. This would be considered an amine. Okay? So this is how you would identify the functional groups. I do want to make note, you can see some of the bonds are depicted differently. So for example, you have this solid wedge or this dashed wedge. This indicates a 3-dimensional nature to the bonds, also known as stereochemistry. We are going to see this in later chapters. Before I end this video, I just want to make a couple of notes about amines and amides. Now, there are different forms for an amine and an amide. When you have an amine that has 1 R group, where R is alkyl, so it's a carbon-hydrogen group, you have a primary amine. If you have a nitrogen with 2 R groups, and you can see I designated one R1 and R2, that means they're alkyl. Right? They could be the same or they could be different. This would be a secondary amine. The third structure I have a nitrogen with 3 R groups attached to it. This would be a tertiary amine. So all of these representations in a molecule would be classified as an amine. For an amide, where you have that carbonyl bonded to a nitrogen, right, you have a configuration where the nitrogen can have 2 hydrogens. That would be a primary amide. Right? If that nitrogen has 1 hydrogen and then essentially 1 R group and the carbonyl, it would be a secondary amide. Right? And then if the nitrogen has 2 R groups and that carbonyl, it would be a tertiary amide. So again, I just want you to have those in mind when you're looking at molecules and identifying functional groups. You will not have to designate primary, secondary, and tertiary at this time. That will come later. However, I want you to be able to recognize these configurations when you see them in a molecule.